Hello everyone, and welcome to today's presentation on quadratic time complexity, or Big O of n squared analysis. In this session, we'll introduce algorithm complexity with a focus on quadratic growth, review practical examples, and discuss the real-world impact of such complexity. Let's begin by defining quadratic time complexity. Big O of n squared means that as the input size increases, the running time of an algorithm grows quadratically. This situation is common in algorithms that use nested loops, where each element is compared with every other element. Recognizing when an algorithm has quadratic time complexity is crucial because it helps us identify potential performance issues, especially with large inputs. Now, what exactly is Big O of n squared? In simple terms, if an algorithm performs roughly n times n operations, its growth rate is quadratic. Imagine a grid where both the rows and the columns represent iterations over your input data. The total number of operations corresponds to the number of cells in the grid. A real-world example of this is a bubble sort algorithm, where every pair in a list is checked and then sorted. Let's write code of bubble sort here. We are going to create two loops to sort the array of items. So let me fast forward it, as our goal is to understand the Big O quadratic notation. We start by defining a function called BubbleSort that accepts two inputs, an array and its size, n. Its purpose is to sort the array in ascending order. Outer loop. Inside the function, an outer loop runs from the first element to the second to last element. This loop ensures that with each pass, one of the largest remaining unsorted elements bubbles to its proper position at the end of the array. Inner loop. For each pass, iteration of the outer loop, an inner loop compares adjacent elements. It iterates from the beginning of the array up to the last unsorted element. It checks if the current element is greater than the next. If so, the elements are swapped, moving the larger element toward the end. Swapping. Swapping ensures that out-of-order elements are repositioned correctly. After each pass, the largest unsorted element is placed correctly, reducing the number of elements that need to be checked in subsequent passes. The use of two loops means the number of comparisons is roughly proportional to the square of the number of elements. Implication: doubling the number of elements increases the operations by roughly 4 times, illustrating the inefficiency of bubble sort for large datasets. To help visualize this, take a look at the animation here. Imagine a grid where the x-axis and y-axis each span n iterations. Every cell in this grid represents one operation. Notice how, if n doubles, the total number of operations quadruples. This visual demonstration reinforces the idea that quadratic growth, or Big O of n squared, can quickly become overwhelming as the input size increases. Let's talk numbers. For a small input where n equals 10, you might perform roughly 100 operations. But if n increases to 1,000, you're looking at about 1 million operations. This dramatic increase highlights why quadratic complexity, or Big O of n squared, can be a significant bottleneck in performance. We'll also discuss how quadratic growth compares to linear growth, and consider strategies for mitigating these performance challenges in real applications. Before we move on, here's a quick recap of BigONotation. It describes the upper bound of an algorithm's growth rate. For example, O(1) represents constant time, O(n) is linear, O(n log n) is linearithm, and today our focus is on Big O of n squared, quadratic time. Understanding these different growth rates is critical when selecting and optimizing algorithms, as it helps you predict performance as your data scales. Let's summarize the key points. Quadratic complexity arises in algorithms that use nested iterations over data sets. While such algorithms can be efficient with small inputs, they often become problematic as data volumes grow. When performance is an issue, consider alternative approaches to reduce the number of nested loops or use more efficient algorithms. This understanding is essential for designing systems that can scale effectively. I hope you got the clear understanding of Big O quadratic notation. If you have any question, you can drop me a comment. On this note, I am stopping over here. See you in the next session.